Hello everyone, welcome to video lecture series of Computer Organization and Architecture. Today's topic is Array Multiplier. In this video, I'll be telling you how to design an array multiplier with the help of two examples. Let us begin. See, when we have to perform the multiplication of the two binary numbers, you have studied about the multiplication algorithm, Booth's algorithm, but when we are talking about the implementation of the circuit, so what is going to happen when you are multiplying two binary numbers, then with the help of the micro operation, the multiplication can be performed, and when we are going to implement the circuit, it could be implemented with the help of the combinational circuits because that is going to form the product bit all at once. And array multiplier, the beauty of this multiplier, the advantage of this multiplier is it is a fast way of multiplying the numbers because it takes only the time which is required for the signals to propagate through the gates which form the multiplication array. There is no more propagation delay. This is a very fast method of the multiplication. So array multiplier, you can define it as a digital combinational circuit which is used to multiply two binary numbers by employing array of full adders and half adders. You must have studied about the half adders, full adders. Whenever you need to add the two digits, you can use half adder, and when there is a requirement to add three digits, then you are going to use the full adders. And the array multiplier about which I am talking in this particular video, this is mainly used for simultaneous additions, frequent additions of the various product terms which are being involved over there. So as I've told you that it is a well-known structure, right? Multiplication circuit, this is based on the add and shift algorithm, and each partial product is generated by the multiplication of the multiplicand with one multiplier bit. See how you can understand it. Suppose I'm talking about 2-bit by 2-bit array multiplier, means multiplicand and multipliers both are having 2 bits. If one number is having 2 bits, B1, B0, and the another is having A1, A0. So what is going to happen when you are multiplying? So first you are multiplying A0 with this particular term. So what would be the first term? First term you will be getting A0, B0, and second term will be A0, B1. Next you will multiply with A1, means you are shifting, right? Shift algorithm. So here when you are multiplying with A1, so the first term will be A1, B0, and second term will be A1, B1. Now you are going to add these two. So here you will be getting this particular term, let us say Y0, sum of these two, Y1, sum of these, this, in case if there is any which is being introduced from the previous stage. This is the output which is Y2, and during the addition at this particular stage the carry may be generated if that is Y3. So you can observe over here when you are multiplying 2-bit by 2-bit, so in the result you may get 4 bits, and partial products are shifted according to the bit orders, and finally you are performing the addition. Accordingly, you have to design the circuit. So for this particular example, you can see in this circuit, this is what 2-bit by 2-bit array multiplier. Now you can observe for the first stage A0, B0, which particular logic gate is going to be used, right? So you are aware with the basic logic gates and or not. So when you are observing the partial products and when you are multiplying, so for the multiplication, if the two bits are 1, then output will be 1, otherwise it will produce 0. It means the basic gate which you can utilize, that would be the AND gate for multiplication, and when both bits will be 1, output will be 1. So here you can observe for the first bit A0, B0, you have used one AND gate, output you are getting Y0. For second stage, you are adding two numbers, right? Then you are getting Y1. So when you have to add two bits, what you are going to use? You can use the half adder. So you can observe the input to the half adder is what? A0, B1, the first term, and the second term is A1, B0. So the input to this half adder are these two inputs. Output will be the sum, and here sum we are saying Y1. and whatever the carry is being generated, that will be carried to the next, right? Carry, in case if there is any generated, that will carry forward over here. So here you are adding this previous carry in case if it is and A1 B1. So there are two inputs to the half adder and the output will be sum and carry. So this is how you can observe how 2-bit by 2-bit array multiplier could be designed. So this is a very basic circuit. Now this is the example. Here I have taken a array multiplier for 4-bit by 4-bit. Means there are two numbers and each and every number is having 4 bits. You can observe the first number A0, A1, A2, A3 4 bits. The second number B0, B1, B2, B3 4 bits. These are the inputs. Output, how many you will be getting? See, multiply bit by bit. First you are going to multiply A0, A1, A2, A3 by B0. See, you are getting this stage. Then you will be shifting one position left and you will multiply with B1, A0, B0. In the next stage, you will be shifting one position again, right? This is how multiplication will be observed. And when you are going to add, how many bits you will be getting at the output? Y0, Y1, Y2, Y3, Y4, Y5, Y6 and Y7 if any carry is being generated. Means you have listed out each and every product term by shifting one position left and then you are taking the addition sum of all these terms. So now you can realize when you are going to implement this particular circuit by using basic logic gates, it would be very much complicated. Though you can design, you can use 4 AND gates for first stage, 4 AND gates for second, then you are using OR gates and accordingly you can implement. But in case if the number of bits in a number going to increase 10, 20, then it would be very much difficult. So how to design that particular kind of circuit? What is the basic background behind that? So for that particular cases, we may use parallel adder, right? How can we use and how many bits of parallel adder? You can observe the sum is being performed at different stages. So here you can observe for first stage number 1 and 2, you can observe 4 bits. Number 2, the sum of this 1 and 2 will be maximum 5 digits. Then it will be added to the next. It means we can use parallel adder. But how we can use parallel adder and how to implement it? Let me tell you. But you must remember that it produces 8-bit sum. Simply just write down all the terms you'll be getting. You will be able to count it out. Total there are 8 terms. Now let us see its circuit. You can observe over here, this is the same example I am carrying forward. The two numbers small a and small b you have taken. Now you can use, here we have taken 4-bit binary adder, right? 4-bit binary adder, first binary adder. So what this binary adder is doing, it is performing the addition of these two stages. Now just observe it. What is the first term? A0, B0. A0, B0 is this. Simply AND gate is being used. And what is the output? Y0. So now you can observe 4-bit binary adder. How many inputs will be there? 4 bits. So here you can observe these terms. Y0, Y1, Y2, Y3 I have mentioned out. And here X0, the first term is being taken directly. So this is what? X0, X1, X2. And at this particular stage, there is no term. So this term is being taken as what? 0. 0 is being taken as X3. Now when these two numbers is being added by the binary adder, we will be getting the sum, which is S0, S1, S2, S3 and a carry, right? So now you can observe, keep observing these two stages. Why not you have just observed from this particular term? And what is Y1? Y1 is the summation of these two terms only. Here you can observe when you are adding these two terms, Y1 you will be getting directly, means this is not going to contribute for the next stage. It means next stage contribution will be from what? S1, S2, S3 and C. So these are the inputs for the second 4-bit binary adder. And the remaining 4 stages are what? This is what? Y0, Y1, Y2, Y3. You can observe these 4 numbers. Next stage and the previous one. Again, when you are adding these two numbers, you will be getting 4 sum bits, S0 to S3 and 1 carry. Again, for the next stage, you can observe this is the sum of 3 bits, right? And you will be getting the Y2. Here, you will be getting the Y2 directly, output of this. And these 3 sum bits, S1, S2, S3 along with C goes to the third 4-bit binary adder, right? And here the next again, this is Y0, Y1, Y2, Y3. This is clear. There is no doubt in this. X0, X1, X2, X3 are the 3 sum bits and 1 carry. Perform addition. You will be getting 4 bits for the sum, which is Y3, Y4, Y5, Y6, and the carry bit may also be there. In case if there is carry, that will be represented by Y7. So how many bits you are getting in the output? Y0 to Y7, total 8 bits you are getting in the resultant. Just you have to remember that whenever you are writing this term, suppose you are observing for this stage. So here what is the term? A3, B3, A2, B3. You can observe A3, B3, this logic gate, A2, B3, this logic gate, A1, B3, this logic gate, A0, B3, this logic gate. Output from these terms have been implemented by using AND gates, and these have been applied. Outputs are the input of the binary adder. So this is how now you can observe this detailed circuit which you could implement by using basic logic gates that have been summarized when you are using 4-bit binary adder. Just you have to remember what is the trick behind it, how the 4 bits can be added, and what is the sum for the next stage, and how it is going to be added to the next stage. Thank you so much for watching this video.